Welcome to the Python programming tutorial series for climate mathematics theory and applications. In this video, we will cover Chapter 3, Basic Statistical Methods, Part 1. We will go over various descriptive statistics that aid us in climate data analysis. Let's begin with diving into some statistical indices from global temperature data, ranging from the years 1880 to 2015. You can download this data at the highlighted URL so you can use it for your own climate data analysis. We are going to be accessing the Pandas module and using the read table method in order to input this data that is in a text file. We are going to point out that we do not have a header in our file and we do have white spaces as our delimiter in this file. We are going to access the values of this file using the .values method on our data that we just uploaded. Then we are going to view a sample of our data, which is going to pop out an array of arrays as seen in the highlighted text. Next, we are going to be going into some descriptive statistics about our global temperature data. We're going to be looking at mean, variance, standard deviation, skewness, kurtosis, and some quantile functions for our data. First, let's get the dimensions of our data. We're going to be doing this by using the .shape method, and we do get an output of 1,647 rows by 10 columns. Now, we are going to only access the second column of the data by using this sort of slicing method. This colon means we are taking all rows, followed by this 2 means we are taking the second column of this data matrix. We are now going to yield the first 6 values of our newly defined variable tmean15. We're going to view the first 6 values by using this certain slicing method. The :6 means we are taking all the values up to the 6th value. As we can see in output array, we do get 6 values outputted. Now, let us go ahead and take the mean of our tmean15 variable. We are going to be accessing the NumPy package with the mean method. We do get a mean value that is highlighted in out5. Next, if we wanted to take the sample standard deviation, we're going to go ahead and stay in that NumPy package, accessing the std, which is the standard deviation method on our tmean15, which outputs a number as seen in the highlighted text. Very similarly, we are going to be yielding the sample variance with the var method, which is also found in that NumPy package. Our tmean15 reports a variance of 0.108. Next, if we wanted to yield the sample skewness of our data, we do need to change our tmean15 into a data frame, more specifically a Pandas data frame. Once we change our tmean15 into a Pandas data frame, we can use the .skew method, which will yield the skewness of our sample. Our sample skewness reports as 0.657. Next, if we wanted to yield the sample kurtosis we are going to have to go into the SciPy stats package, and I'm going to individually import the kurtosis function. That is why this method right here does not need to precede with the package name because we imported this method directly. The kurtosis of our t-mean 15 can be seen in out 9. Next, if we wanted to yield the sample median of our data, we're going to go into that NumPy package once again, accessing the median method on our t-mean 15 data, and we get a median as seen in out 10. Next, if we wanted to yield desired quantiles, we are going to have to make our t-mean 15 into a pandas data frame similar to our skew function. Once we have a pandas data frame of data, then we can go ahead and apply our quantile function. Your parameter in this quantile function is going to be an array of quantiles that you would like to see. The highlighted text is telling the quantile function that we want to see the 0th, the 25th, the 50th, the 75th, and the 100th quantile. When we run in line 11, we do get this beautiful data frame exported with all of our desired quantiles listed next to their quantile that they correspond to. Now we are going to go into correlation, covariance, and some linear trends on our data. We're going to first create a time sequence of our years, which is namely from 1880 to 2015. This line is basically just creating a year sequence in our desired years. Now we are going to be setting up our linear regression, naming it LM for easier access. We are now going to train our model using lm.fit. We are going to fit our model with X variable named in our year sequence. This reshaping of our time variable is necessary for linear regression because we do have to create a matrix as input for X rather than a vector. We are going to be using the response variable of t-mean 15, which is the vector we have been working with our descriptive statistics. Now, once we fit our model, we can go ahead and use our model to make predictions. We're going to label a variable predictions by using the lm.predict function. We are going to have parameters as our X variable time-o. So what this line is doing internally is that it is using our time sequence as X variables in our newly formed linear regression models to make temperature predictions off of. Now we can print some good information about our model. We can see that the coefficient of our linear model is in the highlighted text, and our intercept of our linear model is seen in the highlighted text with a value of negative 13.79. So with these two, coefficient and intercept of our linear model, we can write out our linear model in the form of y equals mx plus b. Next, we're going to go ahead and visualize our linear models. So I am just going to make sure that all previous plots are closed with this function. Now I'm going to be setting up my plot using the matplot library, namely seen as PLT, with x variables time and y variables t-mean. This notation means we are going to be connecting all of our xy pairs with a line in the color black. We are going to go ahead and set our title, set our x label, set our y label as well. Next, we want to overlay our linear trend model on top of our data. We're going to be doing that by another plot function with our x variable, time, and our y variable, predictions. These are the predictions that we retrieved from up here using our LM model to predict. We're going to be connecting these XY pairs with a line, but the color is going to be red. In order to display text, we are going to be accessing that matplot library text function. The first two parameters are XY coordinates, where you want to start your text. The third parameter is going to be the actual text that you want in there. Then it can be followed by the font dict text, which specifies a dictionary that your font will follow. Our font does have a setup dictionary. We are going to be writing with the family name Sheriff, color in red. We're going to have a normal weight and a size of 12 on this text that is in here. Once we go ahead and run the show method, we are going to get this beautiful plot to pop up. All of the black lines are the actual data from our data set, which is overlaid with the linear regression model, which is seen with the red line. Also notice that we do have a linear trend of 0.69 degrees Celsius per century. Next, we could go ahead and yield the covariance of our x and y variables. Just a reminder, our x variable is that time sequence between the years 1880 and 2015, followed by our y variable, which is our global temperature data, dictated as t-mean 15. We are going to access the NumPy package with the cov method in order to yield the covariance. The covariance method will yield a matrix of values. So in order to grab just one value that represents the covariance between time and temperature, we do get a value of 10.62 as our covariance between year and temperature. Next, we can yield the correlation coefficient using the core-cof method on TIMO and t-mean 15. We do get a correlation coefficient seen in out 15 of 0.8275. This tells us that we do actually have quite strong correlation between time and temperature. We can verify this correlation result with the following calculations. we're going to set x equal to time-o, y equal to t-mean 15. We're going to find the standard deviation of x and name it SDX. We're going to find the standard deviation of y and name it SDY. Next, we are going to be taking the covariance between our newly defined x and y and naming it CXY. Now, we can verify our correlation result by dividing our covariance by the product of our standard deviations. This line, our xy, will now be defined as our correlation coefficient. Our xy is a 2 by 2 matrix, so we are going to access the correct value in order to get our correlation coefficient actually exported. Next, we are going to verify the trend result. We can do this by multiplying our xy times your standard deviation of y divided by your standard deviation of x. We do get this matrix outputted. We have a repeating value of 6.98 e to the negative 3 on the diagonal values. This does correspond with the trend that we got before, which is labeled as the coefficient of our linear model. We do get different types of outputs right here, but this value of 0.00698 is confirmed with our actual calculation down here. We can also verify our trend result in another way, dividing our covariance between x and y divided by our standard deviation of x squared. This also can verify our trend result of 0.00698. This concludes Part 1 of Chapter 3, Basic Statistical Methods. In the next video, we will continue with Chapter 3, but take a closer look at some commonly used statistical plots in climate data analysis.